Hello everyone. Our chapter today is about the active ingredient used in parenteral injection and also the excipients used. First, before using the active ingredient in injection, we have to study the active ingredient very well in terms of its pharmacological action, in terms of its crystallinity, if it is crystalline or amorphous. You know that amorphous is more soluble than crystalline drugs. If it is anhydrous or hydrate, again, solubility is important. So you know that anhydrous drug is more soluble than hydrate. If it has polymorphs, some different physical crystals or different shapes, so you know that some of them will have higher solubility or higher stability. We have to study that as well. Crystallinity, hydrate, and polymorphism will affect solubility and dissolution rate, and that's very important if you want to make, or if you will decide to make solution or suspension or parenteral emulsion. It depends on the drug solubility. Partition coefficient also. If you are making an oily injection and you want the drug to be partitioned into the aqueous body fluid after injection, so K or partition coefficient or log B is very important. Also, if the drug is ionized or not ionized, because sometimes ionization may lead to irritation after injection. If the drug is more ionized, also it will be more soluble and fast dissolving drug. pH stability profile, the effect of pH on drug stability, the effect of pH on drug solubility, which pH you will choose for your formulation or for your product, pH 7 or 3 or 10. It depends on the effect of pH on drug stability and solubility. Method of analysis, you have to analyze the drug either by UV or HPLC, high performance liquid chromatography, or by any other way. You have to decide which one is more accurate and precise and reliable. Also, the expiry date of the drug is very important. You cannot make an injection with expiry date 1 month or 2 months, because economically or as a market it will not work, because when you distribute your product to different pharmacies in different cities or different countries, it takes of course 1 or 2 or 3 months. So adjusting the stability and improving the stability and extending the expiry date is something critical. One more thing is the degradation product of the active ingredient. If the active ingredient after degradation may lead to formation of toxic substance or non-toxic, the degradation product is effective or non-effective, or it has certain activity, active or non-active, or it has certain activity. So the degree of pharmacological effect of the degradation product and also the toxicity and safety of this product are very important, because you know that from the day of manufacturing of the active ingredient, degradation happens, but with very small percentage. Maybe after 1 year you will have 2% of the drug degraded. So that's why we need to know this 2% is toxic or safe, is effective or not. With more details, we will pick some of these items. Let's talk about crystallinity and hydrates. Hydrates, it means that the drug is making crystals with water molecules. And we have an example here, sodium cefazolin antibiotic. He has 3 types of hydrate. Monohydrate, 1 molecule drug is making crystal with 1 molecule water. And pentahydrate, 1 drug with 5 water. And sesquihydrate, 1 drug with 1.5 water. Of course, we don't have 0.5 molecule. So sesquihydrate is made like that. 2 drugs, 2 molecules of drug are bound to 3 molecules of water. So the share of each molecule of drug is 1.5 when you divide this by 2 and this by 2. So 2 molecules of drugs are bound to 3 molecules of water. This is sesquihydrate. When we study the stability of this hydrates against humidity of the weather, here we have a graph. On the x-axis here there is a percentage humidity. In the y-axis there is the water content. When we say humidity, we mean humidity of the atmosphere. So 10% it means the weather is very dry, 70 or 80 or 90% it means it is very humid. Humidity is very high. That's of the weather. But when I say water content, it means of the powder. So we need the water content of the powder to be very low. We don't want the powder to uptake water or take water or absorb water from atmosphere. We need our powder to remain dry so it will be flowable, will have high flowability, and will have high stability also. It will not be sticky. But if the powder is hygroscopic, it may lead to stiffness, degradation of the active ingredient. So we need water content to be as less as possible, as low as possible. So when you compare monohydrate, pentahydrate, and sesquihydrate on this graph, you need to understand how to select the best one. If you look at monohydrate, you will see that the water content is the lowest one. So it's the best, but up to 70% humidity, up to 70% atmospheric humidity or weather humidity. After 70% or beyond 70%, what happened to the line? It goes up. So it goes up, it means that the water content of monohydrate after 70% become very high. Sesquihydrate, the line is plateau, although the water content is little higher than monohydrate. But if you continue beyond 70% atmospheric humidity, it remains constant. Pentahydrate is the worst one. From the beginning, even at dry weather, pentahydrate is absorbing humidity. By increasing humidity from 10 to 20 to 30, water content is increasing. So it is the most hygroscopic form of sodium cetazole. So you will find here in the table that pentahydrate is the worst. It has a very high hygroscopicity. Monohydrate and sesquihydrate, you can select between them. If the weather humidity is less than 70%, monohydrate is the best because it has relatively less water content than sesquihydrate, up to 70%. Sesquihydrate is better, especially above 70% humidity, because again, as we said, monohydrate will get more water content from atmosphere, while sesquihydrate will remain stable. Another way to consider before adding the drug to our parenteral injection is to make chemical modification whenever required. We can convert the active ingredient into drug, into ester or salt. Why? To increase the drug solubility or to increase the drug stability, to enhance the drug action, or to avoid irritation. If the drug is irritant, we can convert it to another form which is less irritant to muscles, or to reduce the dissolution rate and make it depot effect, to have a depot action over 1 month, like some contraceptive and some hormonal injection. 1 month, 6 months, 1 year, that's called depot injection. After making it in the form of drug or ester of salt, it needs to be converted to the active form or to the original form, either after reconstitution, before injection, or even sometimes after injection. We have examples from the market. We have chloramphenicol, which is insoluble. If we want to make it in the form of solution, aqueous solution, we need to convert it into chloramphenicol succinate. Same also in case of phenytoin, it needs to be converted to phosphenytoin. On the opposite side, if you want to make sustained release of penicillin, convert it into benzazine penicillin, which will give prolonged action for several days. Another thing to consider in each active ingredient is polymorphism. If the drug is polymorphic, and the word polymorphic, it means it has different crystal shape, for example, cubic and rhomboidal or whatever, and these crystal shapes are different from each other in the physical properties, like solubility and physical stability also. So it's very important to study that, because if the drug is stable in the stable form, it will have different characteristics if it is in unstable form or metastable form, which is something in between. They found that the metastable forms of the drug is having high solubility, but of course less stability. This could be very useful in the powder for reconstitution. You see in the pharmacy that there are some vials that has powdered antibiotic, and it remain powder on shelf life, but before use, the pharmacist or the nurse, they have to add fluid or solution, usually sterile water for injection, and mix it to make solution, so it becomes solution now, and then it can be injected to the patient. In this case, it's very important to have high solubility. So when you add water to the powder, it will dissolve very rapidly. And at the same time, stability is not important because you are adding water just before injection. It will not stay as a solution for 2 or 3 or 5 minutes maximum. So that's why metastable form is important to be used in the powder for reconstitution to make a solution because of its high solubility. At the same time, stability is not important. On the other hand, if you have a suspension, it's very important to have a stable form, because if you have a metastable form, with time, the powder will change from the metastable form to the stable form. And you know that any suspension is formed of two components. Powders that are precipitated, and you can see that by your eye, and the other powder which are dissolved in the fluid or in the solvent and make it saturated. So the suspension is formed in the beginning like that. If you have water and you are adding powder, the first amount of powder dissolve inside water, and then when you add more and more, the drug will start to precipitate. So your suspension is not having powder only, your suspension is having dissolved active ingredient. Small amount are dissolved in water. So if the metastable form after 1 month, after 2 months, after preparation is converted into the stable form is less soluble. So if the stable form is less soluble, what will happen to the dissolved drug? It will precipitate. So with time, this dissolved active ingredient will precipitate over the powder which is present already. This particle will act as a nucleus, and when the metastable changes to stable, some active ingredient will precipitate over the crystal which is present already. So this powder or this particle will increase in size. That's called the crystal growth. So you are preparing your suspension in the size of 1 micrometer, for example, and then after 3 months, more powder will precipitate and it become bigger and bigger, and the diameter of the particle become 10 micrometer. That is very critical because it may not pass through the needle, because we are talking about injection. So the needle could be blocked by the large particle if it is injection, and also if it can pass through the needle, it may lead to severe pain after injection. So as a summary to that, if we have a suspension, it's better to use the stable form, not the metastable form. We should use the stable form, otherwise crystal growth will happen. And if crystal growth happen, particle size of suspension will increase, and this may block the needle and cause pain to the patient. If you have powder for reconstitution, it's ideal to use the metastable form. The metastable form is your choice because it is highly soluble. When you add water to the powder, it will dissolve immediately. At the same time, the low stability here is not a problem because it is by default will be injected just after reconstitution. Another factor which is very important is the pH. pH affect solubility of the drug and affect stability of the drug. So you have to compromise, you have to optimize both of them simultaneously. You have to consider solubility and stability because it is very important. Of course, stability is more important because if the drug is unstable, it will degrade, it will not cause any pharmacological action. But if the drug is insoluble, you can make it in the form of suspension. You can add solubilizer, you can add surfactant, you can add co-solvent to increase the solubility. But stability, you cannot avoid the problem because the drug will not remain active if it is unstable. And it may convert also into toxic substance. So if you look here, the relation between pH and solubility, if that is a drug, like a case, so what is the best solubility here? Oh, sorry, what is the best pH here? The pH that can achieve the maximum solubility in case if you want to make a solution. If you want to make a suspension, you can choose any other pH. But if you want to make a solution, that is the best pH. Here on the left side, on the y-axis, it is not the stability, it is the degradation rate constant. So the lower the degradation rate constant, the higher the stability. So this point, this pH on the x-axis will lead to the lowest log K. If you have very low log K, it means the powder is very stable. So this is the pH of choice in terms of stability. We can also talk here, after talking about active ingredient and its characteristics, we need to add excipient additives, like in the tablet, you know, before that we have lubricant, diluent, bulking agent, and so on. Here also we need to add additive or excipients to increase sterility, or to maintain sterility, to increase stability, control the solution. And the word control the solution here, it means either to increase solubility and the solution rate, or to reduce solubility and the solution rate. Both of them here you are controlling. To also minimize the pain during injection or after injection, to facilitate preparation. For example, if you are making powder for injection and you want this powder to be flowable because you are filling this powder into the vial, so the powder should be flowable, otherwise it will block the equipment itself. So to facilitate preparation and fill the vial, you need to add something also to increase flowability, like tablet. You need to adjust isotonicity, and we will understand in this presentation or in the next one the meaning of isotonicity, and we need to adjust the viscosity also. It shouldn't be too viscous, or also not too loose if it is sustained release. So let's start talking about the excipient one by one. The first one is antioxidant. Actually, oxidation happens in oils and in aqueous solution. Even in oils, we call it rancidity of the oil, change of the color and odor and characteristics of the oil. That's part of oxidation. And it happens also in aqueous solution. It happens because of presence of oxygen, of course, maybe in the headspace of the vial. And the word headspace, it means that is liquid, and here there is air. This air is the head space. So presence of oxygen here in the headspace of ampoule or vial, of course, will lead to oxidation. Presence of heavy metal also facilitate oxidation and act as a catalyst for oxidation in presence of oxygen. Heavy metal could be an impurity from the rubber closure of the vial, from glass, from the solvent, from anything. And some active ingredients also are liable to photooxidation, which is oxidation by light. We have an equation that explains the relation between pH and oxidation. Here on the left side, we have the oxidation potential. The word oxidation potential, it means how much oxygen needed to oxidize the drug. How much oxygen needed to oxidize the drug? That is the oxidation potential. It means if oxidation potential is high, it means what? It means that this drug needs much oxygen to be oxidized. It means the drug is stable. So if we have high oxidation potential, high E, it means high stability. Again, because of high E, it means the drug requires a large amount of oxygen to be oxidized. But if E is low, oxidation potential is low, it means that a very small amount of oxygen could oxidize the active ingredient. And there is E node also, which is again the oxidation potential of the drug in presence of pure neutral water at pH 7. R is the gas constant, T temperature in Kelvin because temperature will affect everything, and OX is the concentration of oxidized form of the drug. Red, it means reduced concentration of the reduced form of the drug. And H plus, that is the concentration of hydrogen ion. So there is a relation, you know, between H plus and BH. If there is more acid, if H plus is high, it means the medium is acidic. It means the pH is low, because you know the acidic pH is from 1 to 6 or something like that, and the alkaline pH is above 7, below 7 and above 7. So if H is high, it means that the medium is acidic. There is HCl, there is H2SO4 in the medium, for example, and if the medium is acidic, pH is low. On the other hand, if H is high, from the equation itself, it means that E is high. If H is high, if the medium is acidic, it means that the oxidation potential is high. What does it mean? It means that most drugs are more stable in the acidic medium compared to the alkaline medium. So the relation between oxidation potential and concentration of hydrogen ion is higher, is a direct relation. By increasing H from the equation, E will be higher and the drug will be more stable. High H, it means what? It means low pH. So that's why the relation between E and pH is inverse relation. We need to reduce pH. Due to reducing pH, oxidation potential will be higher and the drug is more stable. So that's why at the conclusion of Nernest equation, most drugs are more stable in acidic pH compared to alkaline pH. We have example for antioxidant. Some antioxidants are soluble in oil only and some are soluble in water only. So if we have oily solution, we need to use this type of antioxidant like vitamin E, alpha tocopherol, butylated hydroxytoluene, butylated hydroxyanisole, and propyl gallate. If we have water-soluble antioxidant, it's better to use ascorbic acid or vitamin C, or sodium sulfite, bisulfite, metabisulfite. If the medium is alkaline, aqueous and alkaline, so we have to use sodium sulfite. Aqueous and neutral, we have to use sodium bisulfite. Aqueous and acidic, we have to use sodium metabisulfite. The antioxidant level depend on the many factors. We have, for example, the drug itself. If the drug is stable against oxidation, logically we don't need antioxidant. We need no antioxidant or very small amount. So if the drug is stable against oxidation, we can use small amount of antioxidant. If the drug is unstable, liable to oxidation by light, by oxygen, by anything, so it's better to use high concentration of antioxidant to protect the drug. If the headspace above the solution is filled by oxygen, so we have to use large amount of antioxidant. But if this headspace is filled by nitrogen or carbon dioxide, if we replace the oxygen by nitrogen or carbon dioxide, which are inert gas, so the drug is already protected, we can reduce the amount of antioxidant. If we are using, if our vial is single use or single dose or multiple dose, if this vial will be used only, or the dose will be taken at once, at one time, it has 1 milli and the patient dose is 1 milli, so we'll use it one time and then discard it. But if the vial is made to, like insulin vial, is made that the patient is taking multiple doses over several days, 1 week or 2 weeks, it means that the patient will insert the needle inside the vial for several times. Every time you are inserting the needle inside the vial, you are embedding air, and the air contains oxygen. And so if it is multiple dose, we need much antioxidant. But if it is a single dose, only small amount of antioxidant can be enough. Expiration date also is important. If the expiry date is already small, so the antioxidant will not be consumed in 6 months or 1 year. But if the expiry date is 5 years, for example, you will need more antioxidant to make sure it protects the active ingredient all over the 5 years. There are some incompatibility happen between the antioxidant like bisulfite and the active ingredient like epinephrine, to the extent that bisulfite could inactivate epinephrine. So the drug could be inactivated because of the chemical interaction between them, inactivated by the antioxidant like bisulfite. Another type of interaction also, because of changing the sulfite or bisulfite after oxidation, it take one oxygen and it becomes sulfate. And if in the medium, if there is any heavy metal like calcium, barium, or magnesium, of course, heavy metal we have to avoid. But it may be an impurity from the solvent, as we said, from the glass, from the rubber closure of the vial. So if there is any heavy metal present in the medium, this heavy metal will interact with sulfate and form calcium sulfate or barium sulfate and magnesium sulfate, and these salts are insoluble. So again, there are two types of interaction: direct interaction between the antioxidant and the active ingredient, and this may lead to inactivation of the active ingredient. And another type of interaction which is not related to certain active ingredient, the antioxidant itself, after protecting the drug, it will take oxygen instead of the drug and it becomes sulfate. And this sulfate is soluble if it is a sodium sulfate. But if in the medium, if there is any impurity in the form of calcium, magnesium, or barium, or any other heavy metal, calcium and magnesium and barium will interact with sulfate and form insoluble salt, and this will precipitate inside the vial. Thank you, and see you on the next topic.